which covers more about testing of the software. And our speaker is Neil Langmead, who is a technical consultant with Emenda. So, Neil, you should now be the presenter. And we can see your screen, Neil. And we should be able to hear you now.
Okay, wonderful. Well, thanks very much, everybody. That's very interesting. Yes, can everyone hear me? Great.
Yes, go ahead now.
Well, thanks very much, everybody. That was a very interesting basis and platform, actually, for everything that we're going to show now. We've been talking already, we've been hearing about software quality, functional safety, and that's exactly what we're going to be presenting through the tools and methods in this short demonstration. So Emenda, firstly, is a software testing company based in Germany, France, Switzerland, UK, and China. My name is Neil Langmead. I'm going to show you a total testing approach, an approach to software quality that is pulled out of most of the functional safety standards that have already been referenced and is particularly prevalent and useful in 61508, ISO 26262, the FDA standard, SANELEC, and derivatives of those standards. And what we have is something called a total testing platform that is a mixture of static source code analysis, software architectural assessment, software security, and dynamic analysis. You've heard referenced already code coverage, equivalence partitioning, fault injection. All of these
Neil?
Techniques that are aspects of all of these standards and integrated them into one platform. And these are the levels of analysis that we include. Yes, hello?
Yeah, Neil, we lost you for a minute. Carry on. You're back okay now. But yeah. Carry on.
Yeah. Okay. I'm back. Right. So I'm going to jump straight to the demonstration. Firstly, of the dynamic platform that we have, where we can, first of all, decide which functional safety standard that we are applying on our project. So as you can see here, we have D178B for avionics, automotive, for the 26262, industrial, railway, and medical. So we can set which standard we're working to, and then the evidence that will be generated by the tools will be conformant to that standard. So let's start with some software that we might wish to test. And just because it's before lunchtime, I've picked an example where it's a restaurant management system that we're going to shortly test. And just to get you all thinking about lunch and what you might want for your lunch, I'm going to set this project up. We support almost every conceivable embedded software environment and embedded compilers. Most of them you can see here. But for the moment, I'm going to do all my testing and analysis on the host platform. I'm going to use traditional unit testing, which is required by virtually all of the software functional safety standards. As you can see, there are other options. If you're using an agile methodology, we support test-driven development. And of course, all of these solutions also integrate into a continuous integration, continuous development environment. On ISO 262 level, so we can pre-select the code coverage that we wish to obtain, and we can select what source code we want to analyze and our unit that we want to begin testing. That is enough for us to start analyzing the software and performing verification and validation activities. We do requirements-based testing, we do equivalence partitioning, fault injection, and automatic test case generation. So if I look at these options here, we have automated the possibility to insert min, mid, and max test cases, for example. So I can insert those from my software. I can insert a basis path test case where the software will go through every particular possible execution path and derive a test case for that. I have my MCDC test cases for the avionics software standard, D178B. And Also the ability to do equivalence partitioning through our partition test cases. So inside a few clicks, I can actually generate, as you see, 50 or 57 test cases that will execute my software. And that automatically gives us a high level of code coverage. This is even before I've opened the software or even started to look at the requirements. So if I analyze the coverage that's been achieved, I can see that actually through this automatic analysis, I've generated a test harness that gives me 100% statement and branch coverage. I can open that up and I can check that this would indeed satisfy the certification requirements for code coverage and at decision and statement level. Now, of course, that's not testing. We all know that testing has to verify the specification and verify does the software do what the software should do. So for that, we have the ability to insert test cases manually, and you can see that we've actually parsed every piece of data that's required by our software under test and present that in a very easy to use form, so that all that remains to do is for test data to be given either manually or automated from a spreadsheet or from a database or from another external source, such as requirements tools such as DAWs or some of the other ones that you've been looking at today already. So here we can set our test case data. We can say our table is occupied. There are 2 people having lunch today, and as I'm in Germany, let's say I'm the waiter, and I'm in Germany, so I would like a currywurst and pommes if possible. And let's see what options are given to us by the software under test. And we can see that our option here, we have a total that we're expecting, we have a number of guests that we're expecting in our party in the stubs, and we have the details of the order here that we can pass to the software under test. So yes, I would like some soup, and I would like onion soup with a salad, with a green salad. So we're setting up our test data that is expected by our source code. We can leave some of those blank to test that the software does what it should do if data has not been initialized. So we can actually do some error guessing and some fault injection. And once our test data is complete, we can then execute that test case either on its own or in conjunction with the automatically generated tests. So we have a full test harness here that we can use. We also have a requirements gateway that links to CSV for copper separated value, or for integrity, or JAMA, or DAWs, or Polarian, Requisite Pro, or indeed your own custom gateway. So by this method, we have a full system of unit testing and integration testing to the relevant software standard. And the report that's generated is also conformant to that standard, both in terms of the code coverage summaries that are generated, and also in terms of the test case management report that's generated, which will actually reference at the bottom here the particular standard that's been tested to. Now that's the dynamic analysis, and you can see the coverage has been achieved. We also cover the static analysis requirements in our solution, and as you know, many software here we have different possible taxonomies that we can apply to the software. So for example, we can test all of the known buffer overflows, memory leaks, null pointer dereferences, all the common software defects that we find when we're writing C, C++, or indeed Java and some C#. But in addition to that, we have the individual taxonomies mapped to the certification standards. For example, there's the CERT Common Enumerabilities and Weaknesses framework, and the software security standard. Here is the mapping for that. We also have the Common Weaknesses and Enumerability Top 25. We have the DISA-STIG standard. We have the MISRA standard, which maybe many of you have come across, particularly in the automotive domain. We have extremely high levels of automated coverage of this particular standard as well. So we can analyze the software and give you a full report as to how compliant it is to the particular standard, how many defects there are appearing in your software of of these individual types. And for each defect, for example, this is a good one of unreachable code, there is a navigable window that assists the developers in finding out the cause, the root cause of where things are going wrong. There's a detailed traceback, and many of these conditions, actually, many of these problems cannot be found with a visual inspection, a simple 4-eye review of the code. You need a deeper analysis, and that's what we offer here through this traceback. For large software, very large applications, we provide different modules and different views of the software, so that, for example, you could sort on error type, or the owner of a software, or the where the severity of a particular defect. So we have a full defect reporting system. This is on the server. We also have a desktop solution whereby all of this information is pulled down from the server and placed into the developer desktop. So what you're seeing now is a particular source file that I have open in an editor. Let's assume I'm a developer. And we can apply the same taxonomies, the same rules here as we have on the server at a corporate governance level, where we're analyzing against the standard globally on a project-specific level. We as developers now have the ability in our hands to check on the desktop, to check that our source code is free of defects before check-in. So in this way, we are synchronizing the analysis and putting it on the developer desktop at time 0. So now as a developer, I can go through, for example, and see that I have a possible uninitialized variable, which the tool and our solution highlights here, ability of an uninitialized variable, which is critical for an embedded system. We could then fix that here, and as soon as I make the fix in my editor, the analysis is started in the background automatically. So you can see that hopefully on the bottom right-hand corner, the analysis is restarting because I've synchronized with the analysis platform. In this way, we can go through all our defects, fix them before the code is checked in. Many of the software standards also reference software architecture and talk about modularization and complexity. So we can enforce all of these rules as well. We have an architectural solution that measures the complexity and also the dependencies of your system. The way to read this, this matrix, is that components at the top, if you look at the columns, they are using, and if you look at the rows, it is used by. So you can see this common layer here is heavily used by things above it in the hierarchy. For a very well-developed, well-designed system, you would have a lower triangular matrix. The relationships will all be below this diagonal, and that indicates that there's been no architectural clustering or decay of your system, that full modularity has been achieved, and you would be able then to do bottom-up testing. Where you see things that maybe have gone wrong, there are dependencies above the diagonal. These are where layers below, for example, this layer here, is using things above it in data management, measure, and device. So this is kind of a layering problem because the transitive closure of a change is the whole of this subsystem. If I look at this particular problem here, we have number 20, data management layer, is using something, and again we see exactly what's being used, something well above it in the app layer in the measure component. So the greater this distance, the architectural distance, the bigger the effect of this architectural problem is. It basically means the whole of this subsystem is in a cluster, which would go against the advice of functional safety standards, which encourage modularity and so putting all this together, finally standard. Most of the software standards and functional safety standards talk about the need for rigorous programming coding standards. And that may be on a company-wide basis, it may be something like MISRA, but we have the ability through our API to extend our platform. So this gives enormous flexibility to program your own coding rules. If I show you an example, let's define a coding rule for global data. So I would place the code example here into this window. I get the full abstract syntax tree of the source code, and I liked Holger's example at the beginning from Infineon there. Let's say there's a rule that all global data should be called G_Infineon. Then I can actually set this as a rule. Using our API, I could say, first of all, let's find out where the global data is. That highlights for me everything in my system that's global. Then I could ask for all the variables in my system, which gives me exactly the global data that I'm looking for. And then I could call starts with G_Infineon to isolate exactly what it is that I'm looking for. And if I apply this pattern, we'll find that this highlights for us exactly the 3 pieces of data that don't follow my coding standard. So if you are there in a functional safety context and you have a coding standard that you're not automatically checking, you could always send that to us, send that to Emenda, and we can check how many of those rules can be automatically checked and for conformance to the standard. Finally, this is an example of the output that we would produce in a certification context. Here is a report that we would automatically generate from our analysis, in this case for the 26262 standard, and we would generate the list of checkers that have been applied to the software, and in this case, the permitted deviances, permitted deviations from the standard. So, for example, there's a reachable code, but it's allowed because of a forever while loop in the system, or maybe there are special reasons that justify a particular exclusion from the standard. So, in this way, you have automatic certification evidence that you can present to the software verification standard. As I say, automatically. So that's basically everything in a nutshell. Software architecture. We do dashboarding. We do dynamic analysis of the code, including all the techniques that are required by functional safety standards that have already been discussed. Software architecture for dependency analysis. Software security is also there as part of our taxonomy, as well as the well-known software verification standards. And I did say in my dynamic test example, that the example was all about lunch. So I'm hoping that's whetted your appetite for some nice food coming up in the next half an hour or so, wherever you may be. So on that note, I will just present the final slide. We have a full slide deck. A lot of it overlaps with slides that have already been shown this morning, which is why I haven't shown it. But just to return, in conclusion, to the complexity problem that's already been alluded to, the average car has 300 million lines of source code in 2014, which is more than the Boeing Dreamliner. And as already been discussed, the number of states that are in a system in the QNX kernel actually exceeds the number of observable atoms in the entire universe. So we have a real problem with software testing and complexity. I hope that I've shown you some ways of automating that complexity and taking the hard work out of verification and validation to the functional safety standards. And on that note, thank you for your interest, and I will now open up for any questions. Thank you.
Thank you, Neil.